Hey guys, welcome back. We're talking today about Chapter 6, Air Masses and Storms. So basically, we're going to start off with a discussion of air masses, and we'll move into storms. So an air mass is a large parcel of air, a huge area of air. It's going to be hundreds of miles across, and it's going to have to sit still for several days, even weeks. And it's going to sit still over water, or it's going to sit still over land. It's going to be sitting still maybe towards the poles or maybe towards the tropics. So if the area it's sitting upon has certain characteristics, maybe being cold, being wet, being dry, being warm, etc., if the air is there long enough, it will take on those same temperature and moisture characterizations. The area where we get air masses sitting still for a long time are referred to as source regions. So not everywhere is a source region. There are portions of the earth that are adapted to air sitting still and others where air will continue to blow, and therefore air mass source regions won't exist just everywhere. Now there are designations we use for air mass types. There are more than what's shown right here, but these are the ones that will affect the lower 48 states. In addition to these, we have Arctic air masses, which go by the symbol capital A. We also get equatorial air masses with a symbol capital E. So these four are the ones that will affect the US. And these are referred to as MP, CP, MT, and CT. Well, the lowercase m means maritime, and that means it's sitting over an ocean. The lowercase c means continental, and that means it's sitting over the land. And then we get the capital P, that means polar, capital T, tropical. So we have, using those four letters, we actually have four different combinations that we can use telling us if an air mass is being formed over land, continental, over the ocean, maritime, towards the poles, polar, towards the tropics, tropical. So if we look at these individually, maritime polar air masses are going to be cold and moist. So these are going to form, at least the ones that will affect us, are going to form off the coast of Alaska. So that's off the ocean and it's towards the poles, so maritime polar. We also get continental polar air masses forming on the land, let's say in central Canada. So especially during wintertime, these are going to be very cold and very dry air masses, continental polar. Maritime tropical air masses are going to form in the tropical ocean, and for us that means in the tropical Pacific, and these are going to be warm. They're not going to get too hot because of the water not letting it get too hot, and they're going to be wet because warm air can hold a lot of moisture. So these are warm, wet air masses, these maritime tropical. And finally we get continental tropical. These are going to form in the land towards the tropics. So basically for us, that means northern Mexico. And the reason being that Mexico narrows as it goes further south, and we don't get enough land to form continental air masses there. But in northern Mexico, on the US border, we do have the land being substantial in width to support continental tropical air masses, and those are going to be hot and dry. So those are the four air masses that will affect us in the lower states. And if I get rid of myself from here, you can probably see this a little bit better. I'll say goodbye for now, at least visually. There we go. So here we go. We've got continental polar air masses forming in northern Canada. This is a source region for this continental polar air mass. And you notice that they form here, and ultimately the arrows are going to show you which way they will try to move. We also get maritime tropical air masses forming off the coast of Alaska. And again, these are going to be, it says here, cool and wet. It's going to feel pretty cold to us up there, and not so much wet as very moist, because remember, cool or cold air cannot hold as much moisture. But those air masses will swoop down into the mid-latitudes, given the chance. Continental tropical air masses, as was just mentioned a few minutes ago, form in the northern portion of Mexico, especially in the summertime, and those are going to be hot and dry. And if you notice also, the arrows will show that from the source region, they will move into the mid-latitudes. And the same with maritime tropical air masses. These are very warm, very wet air masses forming off the coast of Mexico, in this case in the Pacific, and those will move into the mid-latitudes. We also get maritime tropical air masses forming in the Caribbean and the Gulf of Mexico, and those will also move into the mid-latitudes. So we can see that these areas down here, towards the tropics at least, are where we're going to find our tropical air mass source regions for both continental tropical and also for maritime tropical. And these regions up here towards the poles are going to be the sources for our polar air masses, both continental polar and maritime polar. And you can also see that there's a big hole in the middle here where we don't get air mass source regions. Now the reason for that is this is the zone of the westerly winds, which typically blow pretty consistently from the west towards the east, and they don't allow the air to settle that much in one area for the weeks required for an air mass source region. The other thing to notice here is that what would happen when this cold, dry air was forced into the mid-latitudes to bump into maritime tropical air being forced in the northerly direction to clash with this continental polar air mass. So when that happens, watch out. Cold, dry air mixing with warm, moist air, we can get all kinds of storm activity. So there's your air mass source regions. These arrows are going to lead us to the rest of the discussion. Why is it that these different air masses would move from the source region into the mid-latitudes and create the storms we're talking about, such as this? So again, why are they taking this motion away from the source regions into the mid-latitudes where they can clash and develop into storms? Well, the answer to that lies back in our previous chapter when we looked at our air pressure and winds. And if you recall, the subpolar low, also called the polar front, is an area around 60 degrees north where the air will rise, split at high elevation, again, rise at 60 degrees north and split, and some of that will come back to 30 degrees north. Where that air split up here, we have something called the polar jet stream. And that polar jet stream is a river of air going from west to east, around and around and around the planet. Let's take a look at that. This next slide here. So here is the polar jet stream. Right here, going around backside, come back around again. So from west to east, around and around and around. And what it's separating is very cold air to the north and more moderate or even warm air to the south. So this polar front or polar jet stream located about 40,000 feet up in the air. If you're on the ground, you would be experiencing low pressure of the subpolar low, but you go up in the air about 40,000 feet and you'll find this river of air moving from west to east, maybe 100 miles an hour in some cases. Now, in this diagram on A, so portion A, we see a pretty flat trajectory of this polar jet stream. And that would be more of a summertime position. It's located in summertime a little bit to the north of where it would be in the rest of the year. And the jet stream itself has got a pretty flat trajectory. Now, if we go into B over here, we can see as we get into the spring months or the fall months, we're going to see bends develop in this jet stream. And the whole thing is moving a little bit further south. As the sun migrates, or the direct ray of the sun migrates into the southern hemisphere, so the subsolar point moves into the southern hemisphere, it's going to basically drag the jet stream with it. As we get into the height of winter, we see the jet stream has been moved a little bit further south again, but we get these enormous bends in the jet stream. And these bends are going to move cold polar air into very southerly locations and also move warm, moist tropical air into the same mid-latitude destinations. And since at the surface, this is the area of the westerly winds, the surface winds are going to drive these cold and warm and cold air masses together. They're going to crush them together over time as the whole system moves from the west to the east. The key here is the development of these bends in the jet stream, or bends in the polar jet stream, and those bends are referred to as Rossby waves. Now, Rossby waves are going to not only move that cold air, but they're going to spin the air at high elevation. Can you imagine right here? This is bending, and this air back here is going to spin around and around, in this case in a counterclockwise direction, whereas this air, this warm air, is going to get spun around in a clockwise direction. And this cold air over here will get spun around in, again, a counterclockwise direction. So the upper air, the air about 4 miles above our heads or so, is going to spin around in different directions. And that's going to be critical for setting up our weather patterns. So, a quick definition here. Rossby waves are undulations. That means kind of like a series of bends. So undulations in the polar jet stream. They're mild and more polarward in summertime. They are extreme and get more equatorward in the wintertime. And this is going to allow, in winter, cold air to move south, warm air to move north, both of them into the mid-latitudes. They will get crushed together and basically give us our wintertime storms. As we get into discussion of different storms, we're going to talk about 4 different types of storms. We're going to talk about these winter storms, we're going to talk about tornadoes, we're going to talk about hurricanes, and we're going to talk about thunderstorms. So 4 different types of storms I want you to know about for this class. For each of them, I want you to know, what are they? How could you define what is a winter storm? By the way, the fancy name for those are mid-latitude extratropical wave cyclones. Obviously, you can tell why we just call them winter storms. We also will discuss tornadoes. I want you to be able to define what a tornado is, and a hurricane and a thunderstorm, and be able to tell how they're different from one another. I want you to know how they form. So how does a wintertime storm form? How does a tornado form? How does a hurricane form? How does a thunderstorm form? Where do we get them? Remember, this is a geography class, and the key to geography is a location. So where do these storms tend to form? When do they form? Well, obviously a wintertime storm or mid-latitude extratropical wave cyclone should be forming in the winter. Well, tornadoes are also quite seasonal. Depends on exactly where you are as to which season. But we do say for the U.S. as a whole, there's a specific tornado season, or at least when we get a peak in tornado activity. It's the same for hurricanes, and to be honest, the same for thunderstorms. So where do they form, when do they form, and why are they important? So I want you to know that for each of the storms we'll be discussing. Now for mid-latitude extratropical wave cyclones, these are our wintertime storms, and they're going to develop when we have Rossby waves acting in an extreme manner. So that's going to typically be wintertime. And again, not all winter, but the Rossby waves will develop and be able to spin the atmosphere at different times in the winter, giving us our wintertime storms. They're going to allow the cold air and warm air to mix. And they're also going to form very specific portions of these mid-latitude extratropical wave cyclones, which include a low pressure center, a warm front, a cold front, and an occluded front. Now, if this was a weather class, we would also talk about something called a stationary front, but we very rarely get those in the LA area, so I'm going to skip that. But if you take a weather class with me, we'll talk about more than what you're going to learn in this class, because this is just an overview of how the Earth works. Now, rather than spend half an hour redoing something that I already did once, I'm going to give you this time to look at 1, 2, 3, 4, 5, 6, 7 little videos on your Canvas modules. They look like this. So once you see Chapter 6, Storms Revised, that's a PowerPoint presentation. I want you to look at these videos right here. The most important ones are the ones that say mid-latitude winter storms parts 1 through 5, because that's going to build up and show you step by step how our wintertime storms develop. So go do that right now, and once you're done, come back, continue from here. Okay, welcome back. I kind of goofed there, so I'm doing a little bit of editing. I'm going to redo this section. You should have looked at those videos by now, and in doing so, you'll be able to recognize this view from space of a mid-latitude extratropical wave cyclone, showing the low pressure center, showing the line with triangles on one side of the line. So this is a cold front. The line with semicircles on one side of it is a semicircle. So this is a warm front. So this is showing warm air moving into colder air. It's going to ramp up over that colder air. So low pressure center, cold front, cold air, warm air, cool or cold air on this side. A classic mid-latitude extratropical wave cyclone, otherwise known as a wintertime storm, set up by a Rossby wave. Now the light blue here will also show that we have precipitation in advance of or in front of the warm front. We have precipitation around the low pressure center, because that's an area of rising air. And we have precipitation at and a little bit behind the cold front. So these are the areas of precipitation shown in light blue. After looking at those videos, you should clearly be able to identify those different segments and know this is shown from way up high in space, looking down onto the surface of the Earth, what we call a plan view or map view. This is showing a warm front. Remember that warm air was streaming in from the south, moving off to the east and ramping up over the cold air. So we've got cold air down here. Warm air came up around and ramped up a very low angle, which means that the rainfall is typically ahead of where the warm air intersects the cold air at the surface on a warm front. Whereas a cold front, here we see the warm air and the cold air barreling in. It's coming in very quickly from the west, in our case. It bumps into the warm air and lifts that warm air up very quickly. That's going to develop things like cumulonimbus clouds, whereas warm fronts would be more than likely, the rain from them, to come from nimbostratus clouds. But for, again, a cold front, quick lifting up because this front is very steep. It's going to give us cumulonimbus clouds and pretty heavy rainfall. So the whole thing is going to move off from the west towards the east. The warm air is also moving from west to east, but the cold air is coming in very quickly, and the cold air is always the fastest portion of these wintertime storms. Ultimately, all this warm air is going to get lifted up. Remember, warm air can hold more moisture. So again, what we saw there is that warm front coming in and ramping up over the cold air, and we also saw cold air in the cold front lifting up this warm air along this line here very quickly. So we get thunderstorms along here or heavy rain. We would get a lighter rain ahead of or advance of the warm front. Okay, so in this diagram here, we're showing a number of stationary fronts. And again, I said we wouldn't talk about stationary fronts so much, but within this yellow dotted line, you should clearly be able to identify low pressure centers, cold fronts, a warm front, a very small bit of a warm front, an occluded front. So look, low pressure center, cold front, warm front, occluded front. Remember, occluded sounds a little bit like concluded. This storm is ending as it's like pulling a zipper down here. What we should find right here is warm air. Here, cold air. And here, cold to cool air. I think after looking at those videos, that should make sense to you. Okay, so here we have a cross-sectional view, not looking from space, but like looking across the horizon here, and we see cold air. In our case, it would be coming in from the west. We have warm air sitting in the middle, and we have cool or cold air off to our east. So warm air is coming in from the south, making a right turn, or that's towards the east, and ramping up this lower angle warm front. As that air moves upwards, it will give us stratus clouds, and then even higher will give us nimbostratus clouds, and that nimbostratus will give us that rainfall. The stratus can give us some drizzle, but the nimbostratus would give us rain and drizzle. But to see here, this is where the warm front intersects the ground. The rainfall is going to be in advance of the warm front intersecting the ground because that air still has to rise high enough to its LCL to give us that rainfall. On the other hand, that same warm air coming in gets barreled over by the cold front coming in, which makes that air rise really quickly. Because warm air can hold a lot of moisture, as it rises very quickly, boom, it's going to condense at its LCL, its dew point temperature, and very quickly we're going to get some rain on both sides, but a lot of it behind that cold air. This whole system is going to move from the west towards the east, but the cold air always moves the fastest. So the cold front is going to move as fast. The warm air and the warm front are going to move very slowly by comparison. So ultimately, if this moves fast and this moves slow, this gap is going to get smaller and smaller and smaller because the cold air is going to come in and catch up to the cool air and push all of that warm air up into the troposphere. It's going to cool, and all that warm air is going to rise, cool, give us clouds, rain, and then the storm will be done. Once this cold front catches up to this warm front, we now have what's called an occluded front. I'll show you that in a second here. First of all, here's a oblique view. It's taking a little bit of an angle. Cold air coming into warm air. Lifting that warm air up, boom, some storm activity. Here's that warm front and an oblique angle. The warm front have the warm air coming in, banking up and over that ramp of the cold air and giving us some rainfall over these areas here in advance of the warm front intersecting the ground. So, cold front, warm air sector. In between the cold front and the warm front, we've got warm air. You see it in the cross-sectional view, cold air, warm air in between. And this cold front is going to move the fastest, and it's going to squeeze all of this warm air up and out. Give us a few more days, and it will look, let me take myself out of here, it will look more like this. If the cold air is caught up to the other section of cold or cool air, it's moved in and it's lifted all of that warm air up. That warm air squeezes its moisture out. And in this case, this is representing this portion right up here. The cold front has caught up to the warm front. That is an occluded front. And in an occluded front, all of the warm air has been lifted off the ground. And the storm is about to be over. Occlusion occurs from the top where the low pressure center is, and it's like pulling a zipper down. So ultimately, what's going to happen is this cold air will catch up to this cold air. This cold front will catch up to this warm front. This cold front will catch up to the warm front over here, and so forth. It's going to be like pulling the zipper down. And when that happens, storm is done. So storms have a beginning. Oh, sorry. Getting ahead of myself here. Here's an oblique angle of an occluded front. The cold air is caught up to the other cooler or cold air on the other side, and all the warm air has been pushed up into the atmosphere. This storm is just about done. So I was going to say, all storms have a beginning and an end. For the mid-latitude extratropical wave cyclone, it starts around the polar front, or that low pressure subpolar low, and we start to get some bending occurring. Now remember, that could occur any time of the year, but it's going to be most prevalent and most extreme in the winter time. Hence we call these largely winter storms, especially for Southern California. That's about the only time we get them. Would be late fall into and throughout the winter, and then we get a few more in the spring, pretty much done. But that Rossby wave is going to allow that cold air and warm air segments to move into the mid-latitudes and get pushed together. So we develop that warm front, we develop the cold front, and then we slowly get occlusion from the top down. Ultimately, we get more and more occlusion, and finally, with occlusion, the warm air has been pushed up above the cold air. This is dense air sitting on the bottom. This is lighter air sitting above, just where they want to be. Storm is done. No more rain, no more clouds. We're done. So some questions for you. On a weather map, how are the following shown? How would you show a cold front? How is a warm front shown? How is an occluded front shown? And you should be able to identify those by drawing them or seeing a picture or also describing them. So sometimes you just have to say a cold front, a line on the weather map with triangles on one side. So as simple as that, but no both ways, right? Visual and in writing. Question 2. Why are cold fronts associated with cumulonimbus clouds and heavy rainfall, while warm fronts are associated with nimbostratus and lighter rainfall? So why is that the case? Question 3. Put these in order from fastest moving to slowest moving. Now I've made a mistake here, so you might want to think about this. I want you to put it in the order cold front, warm front, and not occluded front. Instead of that, that should have said low pressure center. So the order I really want you to look at would be which is fastest, which is which is fastest, which is slowest. Cold front, warm front, and low pressure center. Which is the fastest? I better give you the answer since I just screwed that up so badly. So basically, the cold front is the fastest. The low pressure center is a little bit slower, and the warm front is the slowest of all of them. And that makes sense because the cold front has to catch up to the warm front, and it kind of rotates around that low pressure center. All right, 4. In an occluded front, where has all that warm air gone? Where is it? There used to be warm air between the cold front and the warm front, but by the time that occluded front has developed, where did all that warm air go that used to separate the cold front from the warm front? Number 5, what